How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is our next section of Chapter 13, The Nature of Gases. The word kinetic refers to motion. The energy an object has because of its motion is called its kinetic energy. According to the kinetic theory, all matter consists of tiny particles that are in constant motion. The particles in a gas are usually molecules or atoms. The kinetic theory of gases. So there are 5 fundamental assumptions about gases, and if you look these up online somewhere else, sometimes they're broken up into 5 or 6, just depends on how they're broken up, but we're going to go with 5. So number 1 is that any gas is composed of a very large number of tiny particles that are in constant random motion. Number 2, their collisions are perfectly elastic. So what that means is when they bounce off the walls of a container or when they bounce off of one another, they do not lose any energy. Perfectly elastic. Number 3, the molecules are very far apart compared to their size, so far that they can be considered as a point and that they have no molecular size. There are no attractive forces between molecules. Now, this is unlike liquids and solids. There are no attractive forces between molecules of gases. And number 5, the kinetic energy of molecules depends on the temperature. The motion of particles in a gas is rapid, constant, and random. Gases fill their containers regardless of the shape and volume of their containers. An uncontained gas can spread out into space without limit. Think about when somebody sprays perfume or cologne in the front of a room, and maybe within a minute or a few minutes that goes by, in the back of the room, you can finally smell that perfume. The rapid, constant motion of particles in a gas causes them to collide with one another and with the walls of their container. The particles change direction only when they rebound from collisions, so they travel in straight paths. All collisions between particles in a gas are perfectly elastic. During an elastic collision, kinetic energy is transferred without loss from one particle to another. The total kinetic energy remains constant. So now let's talk about gas pressure. Gas pressure results from the force exerted by a gas per unit surface area of an object. Gas pressure is the result of billions of rapidly moving particles in a gas simultaneously colliding with an object. If no particles are present, no collisions can occur. Therefore, there would be no pressure. So an empty space with no particles and no pressure is called a vacuum. The collisions of atoms and molecules in air with objects results in atmospheric pressure. Atmospheric pressure decreases as you climb a mountain because the density of Earth's atmosphere decreases as the elevation increases. A barometer is a device that is used to measure atmospheric pressure. At sea level, so the device on the left, at sea level, air exerts enough pressure to support 760 millimeters of mercury. On the top of Mount Everest, the diagram on the right, at 9,000 meters, the air exerts only enough pressure to support a 253 millimeter column of mercury. So what is happening is that the atmospheric pressure is forcing down on this liquid, which is that mercury, which is then forcing it up this tube. So the stronger or the higher the pressure, the higher up the mercury will go in the tube. The SI unit of pressure is called the Pascal. Normal atmospheric pressure is about 100,000 pascals or 100 kilopascals. Two other units are millimeters of mercury and atmospheres. One standard atmosphere is the pressure required to support 760 millimeters of mercury in a mercury barometer at 25 degrees Celsius. So one atmosphere is equivalent to 760 millimeters of mercury, which is also equivalent to 101.3 kilopascals. Recall that standard temperature and pressure, STP, are defined as a temperature of 0 degrees Celsius and a pressure of 101.3 kPa or 1 atm. So these conversion factors here, these three things, we're going to want to know that these three are equivalent so that we can convert between units of pressure. So that's what we're going to do here. A pressure gauge records a pressure of 450 kilopascals. Convert this measurement to, in the first one, we're going to atmospheres. So like we always do, we start with what we know. We have 450 kilopascals, and we need to convert that to atmospheres. So from the last slide, 1 atmosphere is equal to 101.3 kPa. kPa's are going to cross out. We're left with atmospheres. We multiply that through, and we're going to get 4.4 atmospheres. Now let's convert that 450 kilopascals for part B to millimeters of mercury. So 101.3 kilopascals is equal to 760 millimeters of mercury. If we multiply that through, kPa's are going to cancel, and we are left with 3,400 millimeters of mercury. Kinetic energy and temperature. As a substance is heated, its particles absorb energy, some of which is stored within the particles. The stored portion of the energy, or the potential energy, does not raise the temperature of the substance. The remaining absorbed energy does speed up the particles, that is, it increases their kinetic energy. Think about as you're running around faster and faster, you're getting heated up, your temperature is increasing. That's your kinetic energy. As the kinetic energy increases, the temperature increases. And typically, if you're in a hot room, as the temperature increases, you're going to get a little more fidgety and uncomfortable. Your kinetic energy is going to increase. This increase in kinetic energy results, like we said, in an increase in temperature. So average kinetic energy. The particles in any collection of atoms or molecules at a given temperature have a wide range of kinetic energy. So this is just taking and looking at a random sample of particles. Most have kinetic energy somewhere in the middle of the range. And we use average kinetic energy when discussing the kinetic energy of a collection of particles in a substance. Much like when we would talk about maybe a whole class of, let's say, chemistry students, and we want to talk about their grades. We usually just talk about how the average is doing. We usually don't talk about the highs and the lows. We usually talk about the class as an average. Much like we're doing here, we're looking at a collection of gas particles. At any given temperature, the particles of all substances, regardless of their physical state, have the same average kinetic energy. So the figure to the right here shows the distribution of kinetic energies of water molecules at two different temperatures. The green line shows the lower temperature, and the purple line shows higher temperatures. I just said that, so we don't need to repeat ourselves. So as we go to these next slides, most of the molecules have intermediate kinetic energies and close to the average value. So think about it, that average value is going to be somewhere along that center dotted line. And that looks about right. As we look at this distribution for the purple curve, it's pretty wide, but most of our gas particles are going to lie about this range. If we look at the cold water, it's not as wide. So most of our gas particles are going to hang out around this average kinetic energy. Notice that the molecules at the higher temperature have a wider range of kinetic energy. So that purple curve, that higher temperature, the wider range of kinetic energies is more prevalent with the higher temperature. The average kinetic energy of particles in a substance is directly related to the substance temperature. An increase in the average kinetic energy of particles causes the temperature of a substance to rise. As a substance cools, the particles tend to move more slowly, and their average kinetic energy decreases. Absolute zero, or 0 Kelvin, or we also know that as negative 273.15 degrees Celsius, is the temperature at which the motion of particles theoretically ceases. No temperature can be lower than absolute zero. Absolute zero has never been produced in the laboratory. Think about way back in the beginning of the year, we talked about Bose-Einstein condensates that exist at these extremely low temperatures. We looked at some research and we saw that this is true. Absolute zero has never been reached, but a near zero temperature of about 0.1 nanokelvin has been achieved, but we have never achieved absolute zero. So in review, particles in a gas are considered to be small, hard spheres with an insignificant volume. The motion of the particles in a gas is rapid, constant, and random. All collisions between particles in a gas are perfectly elastic. Gas pressure is the result of billions of rapidly moving particles in a gas simultaneously colliding with an object. The Kelvin temperature of a substance is directly proportional to the average kinetic energy of the particles of that substance. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, resources CD, and pearsonchem.com. Have a good day, guys.